Here we have a problem on AP Calculus BC. That is, we have to evaluate the given limit. So that is limit x tends to 0 positive x to the power sin x. Okay, what is the meaning of having x on the right side top corner of 0? That is, x approaches 0 from its right side. So x approaches the value, that is x is getting closer and closer to the value 0 from its right side. That is, x will take the values like 0.1, 0.01, 0.001, so 0.0001. In this way, x is getting smaller and smaller, so it approaches 0. So, but x approaches 0 only from its right side. So, not from the left side. That is, x will not take the values like negative 0.1, negative 0.01. So, x will not take this kind of values because the question clearly says limit extends to 0 plus. 0 plus, that means x approaches 0 from its right side. So all the values of x will be very close to 0, but all of them will be positive. So the value of x cannot be negative because x approaches 0 from its right side. Okay, so to evaluate the given limit, what I'm going to do is I'm going to do direct substitution. That is, directly I substitute the value 0 for x into this given function. So when I do so, what will I get? So I have to plug in x is equal to 0 over here and here. Then I'll be getting 0 to the power 0. So what is it called? It is called indeterminate form. Okay, in evaluating limits, whenever we get indeterminate form, so mostly the students will think to use L'Hopital's rule. Actually, here we are not supposed to use L'Hopital's rule. So because you have to use L'Hopital's rule only if the indeterminate form is like a fraction, 0 over 0. So if you get an indeterminate form like this one, 0 over 0, then you can use L'Hopital's rule. But here, the indeterminate form, what we get over here is not in the form of fraction. So we are not supposed to use L'Hopital's rule immediately over here. Okay. So now, what we need to do in this one? Actually, in this form, one more thing we have to notice, that is, we have variable at the exponent. In evaluating limits, whenever we have variable at the exponent, so what we need to do is we have to use logarithm in evaluating this kind of limits. So what do we have to do? First, we have to assign a new variable for the given function. So that is, let y equals to x to the power sin x. So now, in the next step, I have to take natural logarithm on both sides of this equation. Then I'll be getting ln y equals to ln x to the power sin x. So why do we have to use logarithm, a particular natural logarithm, in this kind of evaluating limit problems? So because we have variable at the exponent, until we have the variable at the exponent, we'll have trouble in evaluating the limit. When I use logarithm over here, I can use the properties of logarithm, so I can get rid of the variable at the exponent. So once I get rid of the variable at the exponent, so it will be easier for me to evaluate the given limit. So how can I get rid of the variable x if I use logarithm? Here, log x to the power sin x. Here the argument is exponential. We can use a power rule of logarithm. That is, in logarithm, for example, ln a to the power b equals to b times ln a. So whenever the argument is exponential, the exponent can be moved in front of the logarithm, and the exponent over here has to be multiplied by the logarithm. So this is a power rule of logarithm. So we can use power rule and we can move this exponent in front of the logarithm. Further, this sin x has to be multiplied by this natural logarithm. So when I do so, there will be no variable at the exponent. Okay, let me do it in the next step. There is ln y equals to sin x times ln x. Here, look at here. Now there is no variable at the exponent. So for this purpose only we are using ln to get rid of the variable at the exponent. Okay, here in the next step, what we can do is we can try to write the expression on the right side in terms of, in the form of a fraction. So that even if I get an indeterminate form like 0 over 0, I can use L'Hopital's rule further to evaluate the limit. So to write this stuff as an expression, we can use the trigonometric identities. Specifically over here, we can use a reciprocal identity. So because already we know that the reciprocal of sin x is cosecant x. So ln y equals to sin x can be written as 1 over cosecant x times ln x. Okay, so in the next step, ln y equals to 1 times ln x is ln x over cosecant x. Okay, now we have taken logarithm and we have applied the properties of logarithm and we have done all type of simplifications. Now what we can do is we can take the given limit on both sides. So limit x tends to 0 positive ln y equals to limit x tends to 0 positive ln x over cosecant x. Okay, here already we know that logarithms are defined only for the positive values of argument. Even for 0, even if the argument is 0, logarithm is undefined. So here natural logarithm, x is the argument. So the value of this argument, the value of this x has to be positive. So whenever, whether we have natural logarithm or common logarithm, whatever logarithm we have, so the argument of the logarithm always has to be positive. It can never be a negative value. So here in our problem, x approaches 0 from its right side. Already we have discussed this one. When x approaches 0 from its right side, all the values over here taken by x are positive. So this stuff is meaningful now. In case if I just have only limit x tends to 0, so if we just have x tends to 0, x approaches 0 from its right side and left side as well. When x approaches 0 from its left side, the value of x will be negative, then ln x won't be meaningful. Okay, now it's meaningful. So because x takes only positive values, for positive values argument, the logarithm is defined. Okay, now what we can do is we can do direct substitution of the limit. That is, we can plug in x is equal to 0 into this function over here. So when I do so, I'll be getting ln 0 over cosecant 0. ln 0 is undefined, and we have to find the value of cosecant 0. Already we know that cosecant is a reciprocal of sine. So cosecant 0 can be written as 1 over sine 0. So we can get the value of sine 0 either from trigonometric ratio table or unit circle. So the value of sine 0 is 0. 1 divided by 0 is undefined or infinity. So the value of cosecant 0 is infinity. So again, we get indeterminate form. IDF means indeterminate form. Okay, here we got indeterminate form, but this indeterminate form is in the form of a fraction. Since it is in the form of fraction, we can use L'Hopital rule over here. Okay, so when I want to use L'Hopital's rule, where should I use L'Hopital's rule? Which is here we got indeterminate form. You just consider the step which comes right before where we have applied the limit. So this is a step I have applied the limit. You just consider the previous step. So this is a step how to use L'Hopital's rule. When I use L'Hopital's rule, I should never do anything with the stuff on the left side that we have over here. You have to keep this stuff as it is until we finish the problem. So the stuff on the left side. And we have to apply L'Hopital's rule always in the step which comes right before where we have applied the limit. So this is a step, I applied the limit 0 for x. So now we have to consider the previous step over here. In this step, you have to apply L'Hopital's rule. When you apply L'Hopital's rule, don't do anything with this stuff. You just keep this stuff as it is. Okay, let me continue this on the next page. That is, in the next page, I'm going to apply L'Hopital's rule over here. So applying L'Hopital's rule means what? We have to find the derivative of the numerator and derivative of the denominator separately. So here we find variable x in both numerator and denominator. Usually when we have a variable in both numerator and denominator and we want to find derivative, we'll be using coefficient rule. But when we use L'Hopital's rule, we are not supposed to use the coefficient rule. We have to find the derivative of this ln x. We have to find the derivative of this cosecant x separately. So what is the derivative of this ln x? It's just 1 over x. What is the derivative of this cosecant x? Negative cosecant x cotangent x. So already I know the derivative of ln x cosecant x. So once you get the derivative over here, so that's called applying L'Hopital's rule. Let me continue the stuff that is up. Let me apply L'Hopital's rule in this step on the next page. Okay, here we are going to apply L'Hopital's rule. I have taken the stuff on the left side as it is. So we have to apply L'Hopital's rule only in the stuff on the right side. That is, here we have to find the derivative of this numerator ln x and denominator cosecant x separately. Already we know that the derivative of ln x is just 1 over x and the derivative of cosecant x is negative cosecant x times cotangent x. So we have to find the derivative of this one and this one. So that's called applying L'Hopital's rule. So the derivative of ln x is 1 over x and the derivative of cosecant x is negative cosecant x times cotangent x. Okay, here in this step, so we can do possible simplifications, if any. So usually whenever we have trigonometric ratios like cosecant, cotangent, we'll be writing them in terms of sine and cosine, because when I apply the limit 0 or any limit we have for x, we can get the values of sine and cosine easily using trigonometric ratio table or unit circle. So that's why I'm saying that we can write the given trigonometric ratios, so cosecant x, cotangent x, in terms of sine and cosine. So let's do that. Limit x tends to 0 plus 1 over x divided by negative. So cosecant is a reciprocal of sine. So we can write this one as 1 over sine x. And using coefficient ratio, we can write cotangent x as cosine x over sine x. Okay, so now limit x tends to 0 plus 1 over x over negative 1 times cosine x is cosine x, and sin x times sin x is sin square x. Okay, so the next step, limit x tends to 0 plus, we can write the negative over here. So negative, and we can write the numerator 1 over x as it is, and we can change this division as multiplication and take reciprocal of this one. Then I'll be getting sin square x over cosine x. So I'm getting limit x tends to 0 plus negative 1 times sin square x is sin square x over x times cosine x. Okay, that's all the simplification we can do. So we got everything in terms of sin x and cosine x. So even if I apply the limit for x, so I'll be able to get the values of the sine and cosine using a trigonometric ratio table or unit circle. So here the limit for x is 0. So hereafter the positive sign over here will not do anything with the problem. So we can simply apply the, we can simply plug in the limit 0 for x. So negative sine square 0 over 0 times cosine 0. Okay, so sine square 0 means we can get the value of sine 0 first. From trigonometric ratio table, the value of sine 0 is 0, and the value of cosine 0 is 1. But when 1 is multiplied by 0, we get 0. So what is it called? Again, we get indeterminate form. Okay, since we get indeterminate form, actually this indeterminate form is in the form of a fraction. So we have to use L'Hopital's rule again. Already we have used L'Hopital's rule, and again we have to use L'Hopital's rule in the step which comes right before where we have applied the limit. So this is a step I have applied the limit. You just consider the step which is previous, which comes right before that. In this step, I have to apply the L'Hopital's rule. The stuff we have over here on the left side to be kept as it is. So to get, to apply L'Hopital's rule, I have to find the derivative of this sin square x and the derivative of this x times cosine x separately. Okay, let me do this on the next page. Here we have the step which comes right before where we have applied the limit on the previous page. So I have taken this step because in this step I have applied the limit. I have to consider the previous step to apply L'Hopital's rule. So this is a step exactly I have taken over here, and the stuff on the left side is taken as it is. Okay, now I'm going to apply L'Hopital's rule over here on the right side in this function. That is, as I told you already, we have to find the derivative of this one and this one separately. Let me do that. So limit x tends to 0 plus. So let's take this negative. And the derivative of sine square, first we have to do derivative for this exponent. That is, we have to take 2 in front of sine, and we have to subtract 1 from this 2. So 2 minus 1 will just become 1. So it will become just 2 sin x. So far I have done derivative only for this exponent 2. So further, by chain rule, I have to do derivative for this base sin x. The derivative of the sin x is cosine x over. So here x and cosine x are multiplied, and both the terms contain variable. So to get derivative of this one, I have to use the product rule. So as it already I have told you that we are not supposed to use coefficient rule when we apply L'Hopital's rule, but product rule can be applied, like in denominator whenever two variables are multiplied, and I want to find the derivative of the product of two variables, I can use coefficient rule. So I think you're all aware of coefficient rule. So coefficient rule means we have to keep the first variable as it is and find the derivative of the second variable cosine x, which becomes negative sin x, positive. Now I have to keep the, I have to find the derivative of the first variable, which is 1. I have to keep the second variable as it is. So the coefficient rule is I have to keep the first variable as it is, find the derivative of the second variable. The derivative of cosine x is negative sin x. Then I find the derivative of the first variable. The derivative of x is just 1 with respect to x, and I keep the second variable as it is. Okay, let me complete this simplification. So negative 2 times sin x times cosine x over x times negative sin x will be negative x sin x, positive 1 times cosine x is cosine x. So we have the trigonometric ratios in terms of sin x and cosine x. So you don't have to do further simplification. I can apply the given limit 0 for x. So when I do so, I'll be getting negative 2 times sine 0 times cosine 0 over negative 0 times sine 0 positive cosine 0. Okay, here we have, so the value of sine 0 is 0, 0 multiplied by 2, 0 multiplied by cosine 0, everything will become 0 because we know that the value of cosine 0 is 1, but the value of sine 0 is 0. So 2 times 0 is 0, 0 times 1. When 0 is multiplied by anything, everything will become 0. And here, so 0 times sine 0. So we already know the value of sine 0, that's 0. 0 multiplied by 0, it's still 0. Positive, the value of cosine 0 is 1. So 0 over 1, I get 0. Okay, here we can take the stuff on the left side as it is over here. So limit x tends to 0 plus ln y. Okay, now we have evaluated this time we don't get indeterminate form, we get a finite value 0. Okay, let's proceed the rest of the problem on the next page. This is the last step we had on the previous page. So here we have a limit for a logarithmic function on the left side. So using composite function theorem, we can move this logarithm out of the limit. So whenever we have a limit for a logarithmic function, according to composite function theorem, the logarithm alone can be moved out of the limit. So then the next step will have a natural logarithm of limit x tends to 0 positive y equals to 0. So here, this is a logarithmic equation. We can convert this logarithmic equation to exponential form. So to convert this logarithmic equation to exponential form, what I need to do is I have to move this natural logarithm to the other side of the equation. When I move the natural logarithm from one side of the equation to the other side, I have to consider only the base of the natural logarithm. So what is the base of the natural logarithm? It's just e. So when I move this natural logarithm to the other side of the equation, I have to consider only the base e of the natural logarithm. The value which already exists on the other side will become the exponent of this base e. And on the left side, we have limit x tends to 0 plus y. So now we have got the value of limit x tends to 0 plus y equals to 0. Already we have assumed y for the given function. That is, we know that y equals to x to the power of sine x. So now we can replace y by the original stuff, that is x to the power sine x. So we get limit x tends to 0 plus x to the power sine x equals to, and what is the value of e to the power 0? It's just 1. Anything to the power 0 is 1. So I've done evaluation of the given function for the given limit. So the evaluation of the given limit is 1.